Okay, I guess we can get started. My name is Chris Hensey. I have the distinction, I think, of being Ned Mohan's first PhD student from way, way back, a long, long time ago, in the last century. Ned is away at a workshop on teaching power electronics and power-related stuff that I've gone to many times in the past, and he invited me 3 or 4 times this year to go, but it just didn't quite work out. So when I finally said, no, I can't quite swing it, he said, good, come and teach my class on Friday. So, okay. I don't know what's going on in your power electronics class right at the moment, but what I'm going to talk about is electromagnetic compatibility. Which, if you have any Harry Potter fans, this is kind of like the dark arts of electrical engineering. And it's like that because a lot of this, the problems are very complex. They're not really real hard, but they tend to deal with all sorts of stuff that's not on the schematic. You have to sort of sit back and look, make assumptions and guesses, and you're making multiple sets of assumptions and guesses as to what might be happening and why you're having problems or issues and how to solve them. But I'll kind of go through it here. It's a very broad field. There's people, of course, that are specialized and made a career out of this kind of work. And it's something that you deal with kind of everything that you might design. So what is well, let's start with EMC. There's a couple terms that get thrown out. EMC means electromagnetic compatibility. And what EMC, or that term, is trying to do, it's trying to ensure that your equipment, whatever you might be designing, sort of works well in the world. It has to operate without bothering its neighbors. And likewise, it has to work in an environment where there's all sorts of electronic devices out there, and it can't be bothered by the other things that are there. And probably one of the things you might not think about, but it ends up being a problem quite a bit, is your equipment has to operate with itself. There's a lot of noise inherent in things that switch, and the first thing that you have to do is make your equipment just work. And there's a lot of noise issues that you'll come up against and fight. That's not so much an EMI thing as far as being regulated, but that's what the things that protect your equipment from others and vice versa are the same kinds of things that help it just operate itself. And this has just always been a problem. It's always going to be an issue in any kind of electronic design, especially as the speeds of processors go up and the power in power supplies go up, the voltage that things operate goes up, the current that things operate at go up. This is just going to contend to always be an issue that just increases the emissions. And then as things get smaller, the first thing the marketing guys say is, well, why don't we take these things out? What are they? They're filters for noise. Well, we've never had a noise problem before. Well, sure, we've had these filters in there. Well, what do we need them for? We don't have this problem. Let's take them out. And so you always have to fight the marketing guys that look at that kind of stuff. EMI, this is the other side. This is kind of, if EMC is the defense against the dark arts, EMI is the dark arts itself. EMI, that term, the I, is interference, so it's electromagnetic interference. This is basically the other side of the coin. It's when you have a problem, that's referred to as EMI. There's all sorts of things that can happen when you have a problem. I mean, it might be something simple that your processor every 1/1,000,000th calculation makes a mistake and you have error correction and you just get a flag that you made a mistake and you go on. Or it might be, that the thing is, whatever it's supposed to do is just totally wrong, comes up with a wrong result. And sometimes you know that, I expect the needle here to be pointing at 5 and it points at 2. And sometimes it can even lead, though, to failures. Devices can fail. Maybe not directly, but there's some real wide-ranging consequences that can happen that are sort of secondary effects, like if what you build doesn't work for a couple minutes because somebody's using a cell phone next to it. Maybe something bad happens to that person. It's not really direct. The electromagnetic interference directly didn't cause it, but the loss of the information that it was supposed to provide or something did have a very big effect. There's another older term. It's used by people that are even older than me. When I first got out of school, people talked about RFI all the time. That's radio frequency interference. It basically means the same thing. Sometimes people use it to mean specifically that the problem is caused by a radio. And that, back in the old days, there was only a few things that transmitted energy, radio, and then as an offshoot of that, television, broadcast, which is still radio in the way it works. Now there's all sorts of other things going on. I mean, switching power supplies, lots of motor drives, all sorts of things make radio frequency interference. So sometimes people use it now to talk about the frequency range. That's also kind of ambiguous because what is radio frequency? It's kind of anything that's in the hundreds of kilohertz on up to almost anything. Switching power supplies oftentimes now are operating in what is the AM broadcast band. I suppose someday we'll be operating in what's in the FM broadcast band. And then wireless devices, they're everywhere now. They didn't used to be wireless devices when this thing started, EMI started, but now, I don't know, I bet we have about 20 cell phones in this room and who knows what else. That's wireless going on in here. So when you're a designer, you've got this stuff that's sort of in the box. You've got a requirement, a spec that your boss gave you that said, you need to make this widget that's going to do this thing. And somewhere in the beginning of that spec, there's going to be a bunch of little line items that might be calling out a bunch of other requirements that you don't know what they are. You just kind of glance through them because you get to you go down further and look at what it is that you really have to make it do. And so it may not be just you that's doing the design, but this thing may have multiple people working on it. And typically any kind of product has a power supply and it has some kind of digital processing. It has some kind of way of telling the user what it is that it's doing. So there's a display, and the analog is not dead. So there's still analog circuits out there. They may be sensors and things like that. And then of course you're going to have to communicate with the outside world. So you have your I/O circuits, and then you put that whole thing in a box and you think you're done. Well, no, you're really not, because once you get the whole thing to work and work with kind of its own noise, that's kind of the little lines that I was trying to draw here, where the power supply might do something that the processor doesn't like, or vice versa. The processor might be switching so fast that the power supply gets confused. All these things happen, and you work through and get all those things figured out and working. Then there's this whole other array of things that you have to do in order to release an actual product. And it has to work out there in the real world. And the real world is when there are things out there like the other equipment that people are going to use, radio transmitters, radar. You might think radar is not a big deal, but what if you're working on electronics that go in the dashboard of a car? And how many times have you gone through a speed trap? Would you like it if your turd signals just sort of came on instantaneously or something when the cop pointed the radar gun at you? I mean, so that would be a minor thing, but if your car didn't work, like it misfired or something, or it applied the brakes or whatever, all the drive-by-wire functions that are in a car, you can bet that they test with radar coming in and as a noise source. Utility power, we kind of take it for granted, comes out of the wall, it's there, and it's real good in this country, but even here we have all kinds of transients that you have to deal with. They're there, and then you have the occasional things, storms where there's lightning hits the power grid. How do you make sure your design is robust for that? Let's talk a little bit about what actually are emissions. There's two kinds of emissions, and they're related to each other. I don't think you can have one without the other. It's just which way does it show up first, or which one is the largest. There's a radiated emission where what your device might be doing is generating energy that's going through the air and interacts with something else, something that can measure it. Doesn't have to necessarily be causing a problem with other equipment, but you measure an electric field or a magnetic field. Magnetic fields are out there. I personally built the power supply back in the 80s for Cray computers that put out 2,000 amps at 2 volts. And when we turned that on, the oscilloscope that we were looking to check things out, it would tip like this. The screen would turn it off, and the screen would straighten right back out. So there's all sorts of ways to interact with other stuff. Now, the other main one is conducted energy. This is when the energy travels through wires, through a path. The path is through wires and wires, cables. It can be through the power connections, through the I/O connections, through the ground connections. However, there's a wire involved, and of course, current flowing down a wire can radiate, and radiated signals passing through a wire can cause things to be conducted into the wire. So everything's interrelated. And the thing to keep in mind is what frequency things are happening at. We all know wavelength is the velocity divided by frequency. But how that affects that is you always got to keep in mind what the frequency is of the signals that you're talking about. A 300 megahertz signal has a wavelength of about 1 meter. And in order for an antenna to pick up a signal, or for like a slot to let a signal go through it, that starts to happen when the wavelength is about 1/20th, when the physical dimensions of whatever it is you're talking about, something in your circuit, is 1/20th of the wavelength. So at 300 megahertz, an antenna of 5 centimeters could pick up the signal. You don't necessarily build antennas in, but you do put wires in, and 5 centimeters of wire doesn't really get you very far. So, and if you're trying to keep things, high frequency signals in, you have to have it in a metal box that has, holes and slots or whatever it is. I mean, you can't just put everything in a metal box, because you need to get things in and out. You need to get signals in and out if you're going to use it for something, unless everybody's just going to live in there, and it might not be a very popular product. So you got to keep that in mind, and if you're talking about now a 3 gigahertz signal, things become 5 millimeters. Those are really tiny dimensions. In general, though, lower frequencies, things tend to be conducted. If it's a 10 kilohertz thing, it's probably not radiated. Although it depends on your problem. If you're working on, like a windmill farm kind of thing, and you've got wires that are going, several hundred meters or something like that, maybe you can pick up some noise that's radiated at 10 kilohertz. Or you can radiate noise at 10 kilohertz into something else that's got similar dimensions. But sort of in the, general rule of thumb, and rules of thumb are always meant to be broken, but if your problems are at less than 30 megahertz, it's probably a conducted thing. Between 30 and 300 is probably some kind of combination of conducted and radiation. And if you're talking about frequencies that are above 30 megahertz, and there's a slot or PCB, it's probably something that's a small feature in the device itself. So two other terms. We're just talking about emissions. Emissions are what your device is producing. It's that those are the things that are measured to see if you comply with the requirements, and those emissions are things that could potentially disturb other equipment. The other side of that is susceptibility. That's the term that's used for when some other emissions bother the piece of equipment you're working on. Susceptibility is usually kind of a smaller part of the problem from the design point of view, because you try to eliminate the emissions, and a lot of things what you do when you eliminate emissions is make it harder. The design is hardened, that is, to susceptibility. It's not as likely to be bothered by other things. But there are all sorts of little sneak paths and things for how other equipment can interact and cause a problem in your design. So you have to design for both. Thrown in all that, there's some other things. It's not just kind of the electromagnetic signals that are going in and out from I/O cables. EMC and EMI also, the broad area covers power quality issues. The one you're probably familiar with is the harmonic correction, power factor correction. This is considered to be an EMC issue. You have to make sure that your equipment, when you hook it up to the power line, doesn't inject signals back into the power source that would bother other equipment. That's the reason for having those harmonic requirements. And susceptibility, in addition to operating where you're next to somebody that may be injecting harmonic currents, there's all sorts of other things that get lumped in here, which is the power line quality, where there's sags and surges and swells. There's a thing they call electrical fast transient, where they basically force the power line up to a couple thousand volts in a few microseconds, and it decays in like 50 microseconds, and they want your design to operate through that. And there's lightning strikes, which is kind of that same thing, only with a lot more drive behind it. There's another one I didn't put on here, but in military designs, they call it EMP, electromagnetic pulse, which is what happens if a nuclear bomb goes off in not necessarily nearby, but within tens of kilometers or something. You can get a very large electrical disturbance that goes through the air. And military equipment has to be hardened against that. There's another one, which is electrostatic discharge. We all live in Minnesota, so you walk across the carpet in the winter and you touch something and you get that little zap. Well, there's a whole set of specs that cover how you design and how you test to make sure that little zap doesn't cause a problem in whatever it is you're designing. These tend to be, there's a kind of a fun little test that it looks like sort of like a little pistol. They call it an ESD gun. It charges up inside and then discharges, and you touch it to a pin or a shield or something, and you basically zap your device and see what it does. And it can, this can cause problems from just the direct connection. You can blow out sensitive circuits that are kind of high impedance. And also just like putting this little zap into a shield can cause the data that's on the wires inside of that cable, it can all be misread, and your device can still fail, even though nothing electronically fails. It just doesn't operate right. It's upset, they call that. And getting a kind of another level further away, but related to all this, there's some other testing that is usually done in a product level. One is high pot testing. High pot, which is short for high potential. Whenever you have something that connects to a voltage source or power source that has either enough energy, like a battery or something, a 12-volt battery, 12 volts doesn't hurt you, but if you short it out, that can hurt you. A car battery can have thousands of cranking amps or whatever. Or you connect to the utility, where there's a high enough voltage, that can hurt you. There's usually insulation somewhere in the system that protects the user from that high energy source, a high voltage source, and that insulation generally needs to be tested. This is oftentimes a DC test, or it's tested at 50 or 60 hertz, but you oftentimes have to apply across your isolation barrier several thousand volts and make sure that it doesn't break down. And the other one I've got in here is ground bonding. There are requirements for it. When you connect your system to ground, you have to do that in a way that if there is a fault that occurs somewhere, it has to be strong enough to carry that fault current and clear a breaker that is, typically upstream. If this laptop fails or whatever, we don't want it to blow up. We want the circuit breaker in the wall to trip and, not have a fire here in the classroom. Although if we did have a fire, we could stop this lecture now, right? So, but that's another test that relates to this, and it's in general that is considered to be in this family of EMC kind of testing. Another important concept is common mode versus differential mode. This applies to conducted signals, not radiated signals, because we're talking about where the current is flowing. In a circuit, you have generally a wire that sends the signal and a wire that returns the signal. And if you can measure your noise signal on those wires and it's in the opposite polarity, that it's sending on one and returning on another, that's referred to as differential mode. That's kind of the normal thing that we do, or that's all circuits are sort of analyzed differential mode. That's the way we, when you're talking about designing or working, analyzing an op-amp, whatever it is, that's differential mode. That's common mode is the unusual one, and that's where the noise polarity is the same on the signal. That's the two wires that you may be looking at, and that means that there's current flowing somewhere else. There's a third wire. It's usually a ground connection. Every piece of equipment that's going to tie to the utility is going to, have some sort of ground connection that's meant typically not to carry any current. It's a safety ground. And that's why we have the three-prong plugs that the center is ground, or you have the two-prong plugs where the one blade is wider than the other, and that's how you make the ground connection. In reality, signals are both. There's a common mode portion and a differential mode portion when you have these noise issues. And so pretty much all things are mixed, although they tend to be more dominantly one common or differential. And there's sort of a rule, where they call it like the balloon or something. Like if you bring the differential mode signals down, kind of imagine pushing in on a balloon, it pushes out somewhere else. The common mode signals will sometimes go up. I probably should have put this a little earlier, but what I meant to say here was sometimes there are other concerns. It's not just meeting the specifications, but sometimes it's important to your equipment what the function of your equipment, whether what the emissions do. And if you're, this is maybe more in a military thing, if you're making some kind of military transmitter or something, you don't necessarily want it to be picked up by somebody else to know, hey, there's, some people talking on the radio over there, better go see who they are. They might be able to figure out, where you are, what it is you're doing. There are electronics that, people had made that could read the conducted signals of like a monitor or something, and recreate what was on the screen. So people, could know what you were looking at on your computer by doing things like that. Those are obviously very specialized kinds of things. They tend to be sort of military and or some kind of secret clandestine thing. But that's also out there, and some of you might end up doing designs for military applications, and you'll have to, these kind of specifications and requirements are going to go to another kind of more deep level. There's a lot of regulations out there. They tend to try to put them together, and there's been a movement to, over the years, make them all sort of the same thing, although every country tends to have their own set of requirements, but no, there's more of a, let's make our requirements the same as your requirements, so if I make something I can sell in the United States, I can sell it in Europe, and not use these things as kind of trade barriers. But this is just a kind of a short list. In the United States, we have this FCC Part 15. It goes way, way back. It talks about how much energy radiated signals can be. The kind of the universal ESD spec is that one that's listed there, that EN 61000-4-2, and so on. And these are the kind of things that you would see listed, like I said, when you might start this new project, they give you a spec that says you're going to design this thing, and on this first page, it's going to have a little list like this, and you kind of just glance over that because, I don't even know what those things are. They can't be important because they have nothing to do with what my widget's going to do. But you'll have to deal with them. And they're not just a single thing all onto their own. This Mill Standard 461, that has all these subcategories. And so these things that say CE, those are all conducted emissions tests. So, and this is sort of showing what kind of frequency range they're applying over. But your device or whatever, if you have to meet Mill Standard 461, you have to do a test or a series of tests, because again, if it's like a conducted emission in a power line and it's a three-phase system, you have to test it in all three wires and in the ground wire. So it ends up being a fairly big thing to do. And there's conducted emissions, conducted susceptibility, radiated emissions, and radiated susceptibility. So like the radiated susceptibility, you're basically putting your device next to an antenna that's broadcasting at different frequencies and making sure that it works. European standards are like that too. This is kind of a short list of things you might encounter. They all tend to have their own little things, like this fast transient one, for example, has multiple levels where first level there's a transient that might go up to 1,000 volts and not have a lot of impedance, actually has some impedance behind it, so it's not necessarily putting a lot of current in. And then if you're the next level, it might go to 4,000 volts and have a much lower source impedance and be much more likely to damage your devices. The IEEE has some standards like that, and some of those they They apply by regions of the country, which can be kind of confusing. It's how do you design a product to meet, say, lightning in St. Louis when you're going to sell it all over. So you just basically have to do the worst case one. You got to figure out where it's going to go, or work it out with the marketing people. But you have to really figure out what it is you're going to try and do. Another thing that shows up in EMI all the time is your conducted emissions. This is current. It's measured in this unit that they call dB microvolts. Why would you measure current with a voltage? Because that's the way they wrote the specs. The problem that you have when you're trying to look at how things, say, are conducted into the utility is any circuit, if you have a source that's going to drive, the impedance that you connect to that source is going to determine how much current flows. Well, what's the impedance of the utility system? How do you determine that? You can't really hook an ohm meter up to the wall. And if you did, you probably would find different results at different places. Might depend where you are in a building like this. Might depend, where you are in Minnesota or what country you're in. So there's a need to standardize that kind of testing. They came up with this device they call a LISN. That's a line impedance stabilization network. This is kind of a mainstay in doing any kind of conducted emissions testing. What this is that first you put some capacitors across the utility to make it locally sort of a stiff voltage there. Yeah, that does bother the power factor because it makes it capacitive looking back, but that's not what you're testing. You're testing at the output of the LISN. And then from the capacitors you add some inductance that sort of gives you a fixed impedance that your device looks into. And then it's easier to show you a picture or a schematic of one. So they're typically in a box, which is what this is showing. The mains can be 50 or 60 hertz, but it's it's an AC device. That C1 is a relatively large capacitor in microfarads, and for high frequency, maybe like 10 microfarads. But it's a film capacitor that has a very low ESR. And then the 50 microhenries of inductance sort of makes all of the high frequency noise not want to go through that inductor. It would rather take the path through that other capacitor C2. C2 is usually a microfarad or so, but again, it's a high frequency capacitor. But it's combined with a resistor that is 50 ohms. And that goes into the EMI receiver, which could be an oscilloscope or a spectrum analyzer. But if you have your device connected up to the side that says DUT, device under test, your device then produces signals where, at the disturbance frequencies or whatever, it wants to push some voltage or current or whatever back through this into the utility line. So the way this thing is supposed to work is it won't go through the inductor. It'll go through the current will flow through the capacitor and show up as a voltage across that resistor. And so this dB microvolt depends on if you're measuring into 50 ohms or whatever it is, but it's basically voltage across a 50 ohm resistor, and that tells you what the current is. And they use a log scale just because of the frequency range and the amplitude ranges that are there, so that's why there is a dB part. So kind of to summarize, you got your device, and you got to worry about all these kind of things for emissions. You're going to have to hook it up to the utility power, but you have to be nice to the utility in terms of what your device sends back to the utility. The power lines going to your device can radiate, and your device itself can radiate. So you're going to have to test what the device radiates, and then when you hook it up to something else, through an I/O cable or something, you have to also test for emissions that are produced there. So that that's kind of an overview of what the big picture is. Susceptibility is the same kind of thing. On the power line end, you've got all these transients that can happen. Transients also can happen on the I/O connectors where there's ESD, and effects of lightning is also a possibility. Depends on what you're working on. And then the radiated susceptibility where there's electromagnetic fields that are going to be applied to your device, and you have to operate through that. So the typical EMI problem you can break into three pieces. And this is a good way to start thinking about something. If you have a problem, you have a source, something that's generating the signal. You have a path. That's however it gets from where it's being generated to where it's causing a problem. And then you have what is it causing a problem in, and that's the receptor. And your device here could be either end of this, or it could be the path as well. Parts of your device are probably the path. And if you can identify what these pieces are, then that gives you a way to analyze or start thinking about how you can solve that. If on the source side, if you're producing a signal that's bothering something else, maybe there's something you can do to not produce that much of a signal, or maybe there's something you can do with the path side to not let it out to where it is going to bother other equipment. And on the receptor side, same thing. Maybe you can shield wires or something coming in so that you don't pick up the signal, or deal with it once you get it inside and put some clamping and filtering. So in the design process, what you often have to deal with is at the initial design, you don't really know what you're going to do. You just have to kind of guess at what problems you might encounter. But this is important to do. You want to put in some kind of component, some sort of solution for what you guess might be a problem. And you want that in from the start so you don't have to go back and respin circuit boards. So there's a place to put a clamping diode. Maybe you don't know exactly how big or what voltage you need to clamp at, but just take a guess and put a clamping diode across an I/O pin. You want to do things like that. The next level is once you've got a prototype built, you want to make sure it does all the things that you're supposed to do in the big part of the spec. But after that, don't tell the marketing guy that it's done and it works. Tell him you need some more time in the lab, and you got to look at to the best you can if you have to meet a conducted emissions spec, how can you measure what the conducted emissions are with the equipment you have? Get an idea of what it is. Look at how the spec is and see what it is. If you're going to test, say, with a LISN like that, you don't have one, well, find an inductor and a capacitor or something and try and do those tests. Then the last part is the more formal compliance test. That's where you go through, typically you go to an outside lab. Big companies will do compliance testing inside. Little companies are at the mercy of the outside labs. And the outside labs, they're certified. They're kind of, their equipment has been calibrated. Their procedures are calibrated, certified. They in effect, they're experts. They know what they're doing. So you bring your thing to them. You usually have to be there with them because you have to put your widget down on the table and hook it up and operate it. And then they'll do all the testing while you're watching it or you're helping them do the tests. Sometimes you have to interpret whether or not it works or doesn't work. Obviously, if things burn up and go up in smoke, well, then it didn't work, unless I suppose that's what it was supposed to do. But if we think about a flyback converter, this is kind of the circuit that you probably see. This is, again, now all differential mode. I've got the earth connection there, but maybe we don't usually use an off-the-line flyback converter, but this is kind of all it takes. If you have an AC line, you can rectify it, go into a capacitor, and you've got your coupled inductor and a switch and a diode, and I don't show the control circuit here, obviously, but we know about switching this and making a DC output, and this can be a DC power supply. Well, the first thing you might think about is the conducted emissions back into the power line. That big capacitor that was on the front end, if that was a perfect capacitor, there wouldn't be any. But if there were perfect capacitors, there wouldn't be any EMI that we would have to worry about. So you know right off that the capacitor has got an ESR and an ESL, and you want to do some analysis and modeling. You probably need to break it up to high frequency capacitance and low frequency capacitance. Electrolytic capacitor that kind of bulk filters, and then some small capacitors that have low impedances to high frequencies. You can do some analysis, some simulation. You can figure out what current might go back through those diodes back into the utility, and then you can come up with a filter and add a filter there, and get a pretty good baseline design of what it might take to filter the switching noise that's going back to the utility. You want to, of course, once you get a filter, you want to add an estimate of what you think the parasitics are. There's a capacitance that's going to shunt your inductance and let the high frequencies go past it, and there's same with on the capacitors. There's some resistance and inductance that's going to limit the high frequency characteristics of that. But basically, what you're trying to do is make it so all that switching noise stays inside the power supply and doesn't go back, doesn't conduct back through the utility. Then the second step, once you've got that, you might want to deal with these input transients. It's important to have that filter there first because these transients are spec'd as a voltage disturbance. They may or may not have some sort of driving impedance, but if we just hook something up to an ideal voltage source, it's just going to blow up whatever it is if it can't handle that voltage if you don't do something to limit the current. So that differential mode filter, although it's there to, you've designed it, its first job is to stop the switching noise from going out. Its second job now is to provide some impedance that separates the source of this transient from your sensitive circuit. Your FET inside might only take 300 volts and your transient might be 3,000 volts. And so you need to add some components that will stop that transient from producing a voltage that's high enough to cause your FET to fail. And as they say on the bottom there, adjust, tweak, and adjust, because this is an iterative process, especially once you start testing it. These are, even though it's a simple idea, we'll just put the 1,000 volt spike on here, and it has a rise time of a couple microseconds and a decay time of 50 microseconds. Exactly what happens in the circuit with real parts, you have to test it to find out, because you can't really simulate it unless you really know all of the parasitics and kind of the parasitics of the parasitics. So if you've done that, then you might be good on the differential mode. But what about common mode? Where does this common mode signal come from? Every place where you've got a wire or a trace or something, you add some series inductance where high frequency signals would just as soon not go. They would like to go somewhere else. They would like to go to something through a capacitor. In every place where you put one trace over another, you make a capacitor. One of the ones that's a real common one is you have a FET and you need to bolt it to a heat sink. A heat sink is like a great big plane. You get it very close because you want to transfer the heat. It's not electrically connected to the heat sink usually, but sometimes it is. And the voltage on the FET is going to be going up and down several hundred volts. So there's going to be a capacitance there to that heat sink, and that's going to bring currents that are going to, every time that FET switches, it's going to go into the heat sink. The heat sink has to be safe for people to touch, so you're going to want to ground it. Or if you don't ground it, it's going to radiate. Either way, it's going to be a noise source. It's either going to be conducting current if it's grounded, or radiating an electric field if it's not grounded. It becomes a big antenna then. And then that kind of happens all over the place. You might have another heatsink on the diode. In your transformer, you've got windings next to each other, and you make a capacitor between the primary and secondary. So one thing you might want to do is sort of change the way things are routed. If you bring kind of the power lines closer to each other, run them in a circuit board where they're one on top of another, so there's very little loop area in between them. That lowers the inductance, increases the capacitance of those lines to each other, but that can reduce the inductance, so it makes the signals want to stay there and not be coupled outside into the enclosure. You can add a shield where you've got a heatsink. This would maybe be a little piece of copper that you would connect to something that's not moving. On this example here, where the FET is on the bottom side, connecting that to the low side, the source of the FET, that's a relatively stable node. If you had an H-bridge, you would want to connect on the high side that to the drain of the FET, because the drain on the high sides of the H-bridge is usually connected to a DC bus. And that you're going to have capacitive coupling then to something between the heatsink and that shield that's voltage is not moving. And so that there's still capacitance that the FET has to deal with, but it reduces the path. It should be down, flowing around in a little circle, not through the ground of the heatsink and out to the ground of the system. How you wind a transformer, this isn't necessarily the best way to do it, but as you wind a transformer, you can do things that change the capacitance. So if you have a bobbin, and say you've got these here 7 turns, and you start, you wind 4 turns, then you come back and wind 3 more turns on top. Pretty simple winding. That's one way of doing it, and that's pretty straightforward. If you think about, well, each turn to another turn has some capacitance, but ignoring that and just looking at where it's turns that are not one adjacent to each other voltage-wise, you would have a circuit kind of like shown on the first one there, where turn 1 and turn 7 are very close to each other. So they're going to have a capacitance because they're parallel to each other for some distance. But you're applying a large voltage across that capacitance. And so the capacitance may not be that great, but a large voltage across the capacitance means there's going to be a lot of current flowing in that capacitance. So if you wind it the way it's shown on the right side, where you do 2 turns and then 1 on top and then another one further over, that would be harder to wind. But then you get the sort of the capacitance structure that's shown on the right side, where you have capacitors that straddle a couple of turns, but not necessarily the entire voltage of the transformer isn't going through one capacitor. And then you've got your effects to the secondary windings to consider. There's capacitances to the core, capacitances to if there's a circuit board underneath, sometimes that's an issue. You just sort of got to make a picture, draw it, analyze it. And again, this is another one of these things where you don't really know what that capacitance is. You don't really know if, there's no thing that says, well, 20 picofarads causes a problem, but 18 does not. You just have to take some of these guesses and try to anticipate what's going to be a problem and then see what you can do to fix it. So common mode noise, if we look at a filter, in this case, we've got our noisy circuit. It's somehow capacitively coupled, maybe it's through that heatsink, to the frame of your device. And we've got some power line filtering, but the power line filtering isn't very effective. If the same signal is applied to both sides of a capacitor, nothing goes through it. It's kind of like it's not there. It is going through those inductors, but the voltage drop you get across the inductor depends on what the voltage in the rest of the loop is. If that is a relatively large impedance at that frequency compared to what your inductor is, that inductor really isn't doing much for you either, and you can get currents going around in this loop. The loop could be through through a ground wire that's in your power cord, or it could be, depending on how things are grounded, it might actually really be through the ground. The white wire in the wall plug is at the same potential as the green wire. The common and the ground are at the same potential, but they're tied together at the panel, which when you plug into the wall here, where is that panel? It's in a basement somewhere or I don't know where it is in this building, but it's not really right next door. It's got some distance. It's probably really a good low impedance, is a fraction of an ohm or something, and that's that bonding kind of resistance that's important for blowing a breaker. But at high frequencies, if you're talking about a signal that's up at 5 megahertz or something, that wire going down to that panel might as well not be there. It's going to look like a big inductor. So that's going to let this voltage show up at the input of your device, go through that LISN, go through those little capacitors, show up as a dB microvolt reading that you're going to get. So there's this other class of filters which are called common mode filters. What you do in a common mode filter, the heart of it is a common mode choke. Common mode choke looks like a regular inductor, except it has two windings, and not that regular inductors don't necessarily have two windings, but they're wound such that the normal current going through it, the current that's bringing the utility into the circuit, cancels out. So there is no net current flow from that, or no net induction in the core. But for currents that are going through in the direction of the arrows, then it looks like a large inductor. And so the current doesn't want to go through that inductor. Now it has a reason to want to go through the capacitor. Those capacitors are center tapped to bring the current to the frame, which is where that little path is. So you're trying to keep all the currents flowing on the inside. I think we're about out of time, right? So I kind of explained. Ned said I should give you some problems. So I have no idea if he's actually going to ask you for turn in any homework or anything like that. But the first one is if you have an IRFP 460, which is a part you can look up on DigiKey, and you clamp that to a copper heatsink through an insulating pad that is 0.125 millimeters thick, and that's switching 400 volts at 250 kilohertz, how much current is going to flow through that? So that's basically figure out the area of it, the capacitance, and what the other part of it is the switching time, which you can get an estimate of what that will be on the data sheet for that part. So the second one is if you take this core, which if you do a Google search, I think you can get a data sheet for, and put 15 turns or two 15-turn windings on to make a common mode choke, how much inductance will you get? And I don't know if these the slides, are you going to send them to everybody or?
Yeah, I uploaded them on Moodle.
Okay.
Yeah.
So, I guess any questions? Looks like maybe we have a minute, or maybe I don't know what time was specified. Already over. I'm sorry.
55 when it ends.
All right. I do have my email address on there. If anybody has any questions, please feel free to send me an email. I'm sorry for keeping you over.
Thank you. So we're using like a motor drive to have one. So it's a ton of noise.
tests yet?
It's like, you know, high public frequency.
No?
And so
When do you think we'll get it back? Over the weekend?
yeah, it was working fine, but only on startup. So it was not lost. And then after the motor ramped up and it got kind of like a steady state, the CAN bus was fine. And so I'm not really